Nope, still the same. Okay. Okay, I'll get started. Thank you everyone for joining. Thanks, Stephen, for the introduction. My name is Akbar. I'm a staff software engineer at Intuit. So today's talk is going to focus on how did we leverage Elasticsearch to solve for search aggregation and time series use cases. So what is Elasticsearch? So Elasticsearch is basically a search engine on top of Lucene. Over the years, its usage has changed. It started as a solution for full text search on top of Lucene. It evolved into event data and metrics, and it's heavily used today in logging and log analysis, and a lot of usages are on that. It's also used for visualizing data. It has a nice tool called Kibana on top of Elasticsearch, wherein you can create dashboards and you can analyze the data that you have. Today, we are going to focus on search and the event data areas. So let me give a quick context of the product that I work on. It is called Quickbooks Online. It is by the company called Intuit INC. Small business accounting software by which you can track your income, your expenses, inventory. You can pay bills. You can prepare your taxes. You can see your business insights and take decisions based on that. You have automated workflows and integrations. So for example, you can connect to your bank. You can connect to Amazon, eBay, Etsy, if you're selling your products on that. You can also connect to your accountants so that they can help you manage your books. So the goal basically is that QuickBooks user or a small business owner can concentrate on the core area, which is their business, whereas the back office stuff, such as accounting, bookkeeping, can be done in the background. So let me quickly share the product. So as you can see, this is the UI. Some of the areas, as I shared, is banking, where you can download or connect your bank and download your transactions. You can have your customers, which are the people that you sell your products and services to. You have invoices that you create for them. The other area is expenses. So you have vendors whom you purchase things from, and expenses are bills and purchase orders, etc., that you create. There's a lot more, like you can create reports and stuff like that. But for now, this is just the context that is enough to understand the talk that we have today. So let me go back to the slides. So QuickBooks Online is kind of a 15-year-old product. So it was not built with the modern architecture. It's one code base. It's the monolith with everything, all domains in it. So customers, vendors, sales, purchase, everything is in one. A few years back, we started on the journey of converting it to microservices so that we can better scale our teams. We can have the velocity with which we can grow and provide features to the customers. So let me go through some of the principles that we used to go from monolith to microservices. The most important one that we used was domain-driven design, or DDD. This basically means that you organize your business in terms of domains. A domain has a context wherein you talk about a model. You have a ubiquitous language that you use for that model. You have teams that are focused on that model. There are experts for a particular domain. In this case, you can see there's a delivery domain. You have an order, you have product, you have customers. This domain generally, or a bounded context, translates into a microservice. So in terms of QuickBooks, if I give you an example, it would be we have a customer management domain, we have a vendor management domain, we have sales as a domain, we have purchase as a domain. So this helps us creating microservices, creating teams around that, and creates ownership, accountability based on domains. There's a really good book, which I highly recommend you guys to read, is by Eric Evans, which is called Domain-Driven Design. And that helps us to design software around domains. The second principle is event-driven architecture or event sourcing. So event-driven architecture basically means that your microservices communicate with each other in the async fashion. API calls are generally the way that for the past. We are going into a microservices architecture where they communicate using events. There is a middleware, which is called as an event bus or a broker. And some of the technologies out there are Kafka, Rabbit. There is Pulsar these days. There's ActiveMQ, which has been there for a while. For our use case, we are using Kafka. Event sourcing means that the changes that are happening in a microservice, they are organized or sequenced as a list of events. So for example, giving you an example of QuickBooks, say we create a customer, we update a customer, we delete a customer. So those are a sequence of events. Those are communicated as event models, which other microservices that can then subscribe to. The third principle is basically polyglot persistence, and this is where we're going to focus on today, is using the right technology for the right use case. So as we evolved from a monolith where we were on a SQL database, we use the SQL database to provide search, to provide time series capability, to provide aggregations. It was not the right choice. We were forced to use it. We did not get the performance that we wanted. We were tightly coupled, etc. So moving from that to using Elasticsearch as the right engine to build those use cases. And the fourth one is data democratization. This basically means that the data is available for anyone and everyone to use. There's no restrictions on the data. There's no gatekeeping on the data. What this does is it provides the data in the hands of data analysts, data scientists, and fraud scientists. So they can build models on top of it to basically provide capabilities without any restrictions. Data democratization is very important these days for big data so that it can be leveraged and the real harness of data can be leveraged. So given these principles in mind, I'm going to talk about 3 use cases that we used Elasticsearch for. The first one is universal search. So this is where we wanted to provide a single place where the small business user can search for anything in their company. They can do type ahead search. They can see what it matched, so providing highlights on top of it. They had, as I said, they wanted to search on all the data, on all the entities that they had. And this was in a scope of a company. Now, when I talk about a company, as I showed, a small business has a company, they have their customers, vendors, transactions, etc. And they want to search on that bounded scope. Let me give you a quick demo of it. So this is what I meant. So they can search for their customers. In this case, I have a customer called as demo. So as you can see, it shows you all the transactions. I can search for amounts. I can search for addresses. So it will give you the address for the customer, the transactions where the address was created and stuff like that. So going back. So the important thing to realize here is that our data is not something that is moving. So in terms of the data is always there. So as the company grows, as the data grows, we have to persist all the data. So we cannot get rid of data, which is generally the use case with logging and log analytics, where you can discard the data, which is say 3 months old or 6 months old. So our data keeps growing over time. So the performance and scale is something that we need to care about. So let me talk about some of the learnings that we had, and these are some of the design concepts with Elasticsearch that we used. So we had to extensively do follow me homes with customers to see how do they use the data. So some of the things are, they wanted type ahead. So as they type partial data, they wanted to see results. They would want to see results when they start typing from the start of the word, or they can start typing from the middle of the word and they still want to see the data. So that help us use some of the features in Elasticsearch. Also, who searching on the data. For example, there can be admins who can search for the data. There can be only given specific access who can only search on part of the data. Sorry, can you guys still hear me?
I can hear you, but your screen went down.
Yeah, sorry. I'll start again. Can you guys see?
Yes.
Okay. So I was at some of the features for Elasticsearch, edge n-grams and n-grams. So in this case, as you can see, as I start typing CVS, you will see anything that start with CVS, right? So this is edge n-grams. Versus n-grams, where users would have uh, vendors or customers who would be CVSs from a lot of locations, right? So the way they would save their data would be CVS at Beverly Hills or CVS at some address. So what they would search by is, say, Beverly Hills or say First Street. So they would start typing from the middle of the word and they would still want to see results. So we had to save the data or analyze the data in a way in Elasticsearch so that these use cases can be solved for. The second is static versus dynamic mapping. So think about it as your data comes in and you store it in Elasticsearch, you can provide a fixed mapping to Elasticsearch where you can say, hey, I have these 10 fields and we only want to search, we only want to save these 10 fields. So for search, we basically had to restrict it to only certain number of fields that we want to search on. And this is for the specific reason that over the time, we wanted to solve for scale. We did not want to provide search features on all the fields that were coming, but only on certain number of fields because the customers only wanted that. And this was intentionally done. When I talk about the other use case about aggregates, we actually save all the data. And in that case, we use dynamic mapping in that whatever you pass to Elasticsearch, it's going to analyze the field and it's going to save the field based on the data type that it has. Versioning. So Elasticsearch provides different kinds of versioning. So it can do its own internal versioning. So if you don't provide any versioning, it can use its internal versioning to increase the version of the document. Um, we used external versioning because we were dependent on the versioning that is coming from the source system. So for example, when you create a document, you have a version 0. When you update it, you have a version 1. Now, since there is a middleware, which is a broker in this case, you can get out of order messages. Therefore, we want to only save the latest data that we have. So we use versioning and we only save the data that is the latest version. The next learning is how do we provide searches on certain fields. So for example, on the left, you have dates. So QuickBooks is used all around the world. We have different date formats. The US uses month, date, and year. Uh, Something like UK would use a date, month, and year. So we had to provide custom analyzers, which you can do in Elasticsearch, um, to provide searching on DDMMYY or MMDDYY, etc. The second one on the right is phone numbers. In the US itself, you can save phone numbers in multiple different ways. So the data coming to us would be in multiple ways, and the users can search the data in multiple ways. To solve for that, basically, as you can see, we got rid of any special um, characters like hyphens or brackets. We saved the data as a string of numbers. And so for indexing and for searching, we stripped everything and we only searched on numerics. So that way, any pattern that the user provides, we can provide searching on that. The next one is to decide whether you want to solve something at index time versus search time. So in this example, as you can see, there is an invoice which has a customer ID on it. And then there's a customer document, which is a separate document and which has a name called John Doe. Now, when the user starts typing for John Doe, they want to see the transaction or the invoice in this case that they have searched on. So what we had to do was at index time, we took the call that we are going to persist the customer name with the invoice so that at search time, we don't take the hit of performance. Otherwise, we'll have to do some kind of join between the two documents to provide this capability. So we did this index time so that the search is faster. So we had to take this call. The other was thriving on reindexing. So this basically means that in Elasticsearch, if you want to change a mapping or you want to change analyzers, you can't do that once the data is saved. So when we had to migrate from an on-prem to AWS, when we had to change analyzers for a certain field, or we had to introduce index sorting, we heavily relied on reindexing. And we had to become experts at reindexing because you cannot predict to a certain point, you can predict what your data is going to look like, but your use cases will change. So it's really important to get good with reindexing. So you can take advantage of changing use cases. You can reindex the data from one index to the other as years go on. The last one is basically taking advantage of hostage infra. Today, there are a few options. You can self-host your Elasticsearch either in your own data centers or on cloud, or you can take advantage of managed Elasticsearch, either Elastic as a company provides that or AWS provides that. We at Intuit use AWS Elasticsearch, but some of the big advantages of hosted solutions are that you don't have to worry about managing them. You can focus on building core features on top of Elasticsearch. Scaling, shrinking of nodes becomes really easy. For security, we had to do AMI upgrades if you self-host it. And Elasticsearch, as you might know, starts rebalancing when you do these upgrades. So when you use managed, all of this is taken care of and you don't have to worry about it, giving you great velocity, and the team can focus on building core search features rather than maintaining the infrastructure. So the second use case I would like to talk about is data aggregation. So think about it as we go into microservices and as we go into different domains. Let me take an example in this case. So on the left, you see that we have a customer list as I showed before, you can have a customer which has addresses, phone numbers, etc. However, as domains, address is a separate domain than customers. But in the list view here, you have to show both of them together. On the right, you see invoices, where invoice is a separate domain than a customer. It only has a reference to a customer. It doesn't have the details of a customer, like the name, the address, etc. So we had to design a solution where we can provide these aggregate views. Entity resolution comes as part of this. So for example, to power the view on the right, you just have the ID of the customer and you have to resolve it to the name. So in this case, if you look at the line number 3, you have to know that the invoice, which is 1020, has Harry Potter as the name of the customer, wherein the data for the invoice would just have Harry Potter, which has an ID of 123 or something like that. We were getting billions of events a day. And as I said before, we have to persist all the events that are coming in. We cannot discard it based on time. And this all had to be done in near real time. So the users would create something on the UI and they would want to search on it. They would want to see it in a list. And this all had to be done in near real time, wherein there was a middleware, which was Kafka, which is async. So the architecture looks something like this. You have raw events that are coming in from multiple sources, multiple domains. We transformed it, we stored it into Elasticsearch, and we provided APIs on top of it to serve all these list use cases or aggregate use cases that we had. This is very simplistic view, but there is a lot more in detail. We had to design and performance test and scale Elasticsearch for a long time. We had to spend about a year on doing this to get it right. So talking about scaling, throughput, and performance. So currently we are on about 24 nodes. We have about TPS of about 20,000 per second, which is the indexing rate. And again, we cannot discard any data. This is just adding new data. And the indexing latency is less than 10 milliseconds. So some of the learnings that we had is there's something called as routing in Elasticsearch, which is very important. So in our case, as I talked before, everything is in a context of a company. So we use this company ID, which is a numeric number. And in this case, just an example, it is user 1, to route the document to a shard. So what this does is your index requests, your search requests always go to a particular shard. So this helps you with scaling because your requests don't go across multiple shards. And this restricts it to a particular shard, and it helps you to scale more. And it gives you a really good design. And because generally these companies that we have are balanced over time in terms of the numeric numbers that they are generated, we will see equally sharded data, equally data across all the shards. And so this was really a core design principle, which was routing that we used. We had to have multiple indexes per entity. And this was basically to solve for the size of a shard. So once your shard goes beyond a certain limit, it doesn't scale. So the limit is about 30 gigs to 40 gigs. So in order to solve for that, for a particular entity, for example, a customer index or a transaction index, we split them up into multiple indexes. We use some kind of hashing algorithm to determine which index would the data go to. And then we saved into that. So this, again, was used to scale and performance for Elasticsearch. As I mentioned, we had to resolve entities in order to show a unified aggregate view of the data. And in this case, we decided we are going to use query time resolutions instead of index time, just because it was not very sensitive in terms of the SLAs, because it was a list use case. And also because just maintaining at index time, just maintaining these or writing these uh, entity resolutions was really taxing on the cluster. So we went with query time entity resolutions. So for example, in this case, if Tom Hanks has an address ID 1 and the address ID is a separate document in a separate index, at real time or at query time, what we would do is first we would fetch the data for Tom Hanks, and then we would resolve, hey, what does entity address ID 1 stand for? And in that case, we would fetch the address, which is 1234 Beverly Drive, and we would the API would provide a unified view. Batch save is another really important tool that you can use for Elasticsearch. It is really scalable when you use batch saves rather than saving individual documents. It scales 10x if you use batch save. Using Kafka for performance testing, this is basically to test the scale of Elasticsearch at 10x, 20x precise. The real-time data that you get is can only provide you a certain performance test. So what you can do is once you have Kafka data for a certain number of time, and you can tune in Kafka how much days or months do you want to store the data for. You can set your offset to earliest, and that will basically get you pump the data from the start of time, and that will give you a really good performance test that you can do against Elasticsearch. So that was the second use case. The third use case that we're going to talk about today is audit, which is basically a time series use case. So what is audit? So in general, is just a chronological events that happens.
Excuse me, Akbar, you have
yeah.
about 5 minutes left.
Okay, thank you, Stephen. I'll try to wrap it up in 5 minutes. So in terms of audit, so this is really important for a small business user, because they would want their accountants to know what they are doing in their data. As an admin, I want to know what my users are using the data for, or they are doing which operations. And importantly, for audit purposes, like if they get an audit from IRS, for an example, they can provide this to say, hey, this is what is happening in my books. And as you can see, this is basically a sequence of events that are happening based on time. So on the right, you can say a user logged in, they created an invoice, they edited an invoice, they created a tax group, they edited a customer, etc. So basically, it shows you who did this operation, what operation did they did, when did they do this operation, and maybe some details as which IP address was used, and etc. So this looks like a classic time series use case, and Elasticsearch provides really nice capabilities for you to store time series data. So this is kind of a high-level architecture. You have various services pumping data through Kafka. Audit sits downstream to these services. It listens to all these events, and it saves to Elasticsearch. So what are some of the features that we used for Elasticsearch? So one is it's a time-based query patterns. So we used rollover indexes. So you can roll over based on time. You can roll over based on size. We use time as our rollover criteria. And so you can say you can roll over every month, every day, every year. So as the data gets old, it is less frequently used. So that provides you performance in terms of indexing and querying. Index sorting is another thing that we use, because you have to sort. The query is generally sorted by last updated timestamp. So it's always in the descending order. Store versus index is another thing wherein we we don't actually index the payload that is coming in. We only store it. So that is important because Elasticsearch has a threshold of how much you can index. It will also affect your performance. And we don't need to necessarily index it. We just need to store the data as is. And it provides you a really nice feature on the right. You can just say enabled equal to false, and it will just store the data, not index it. Cost of hosting / maintenance. What we did was AWS Elasticsearch provides a feature called as Ultra Warm, where it saves the data in S3 so that you don't have to pay for the cost of live data on, say, for example, an EBS volume or even instant storage. So based on time, you can say, hey, last 3 years of data, only keep 1 year of data in EBS versus put 2 years of data in S3 because that is less frequently queried. And AWS Elasticsearch will, on its own, if the query goes beyond that 1 year, will fetch the data and provide search results. So in summary, we solved for three different use cases with the same database, but using different features that it provides. So pick the right technology for the right use case, not just because it's a cool technology, but if it fits, yeah, use it. Elasticsearch is really, really powerful. It can be operated at an insane scale if you design it correctly. So we have to spend a lot of time beforehand to know your use cases in order to design it correctly. For performance testing, if you use Kafka or any replayable mechanism messaging system, then you can performance test Elasticsearch easily. Using managed solution for Elasticsearch will save you time, resources, and you can focus on your velocity and solving for the core use cases. Yeah, that was it. Thank you so much for attending the talk, giving me a chance to talk about our use cases and how we solved using Elasticsearch. And ping me on LinkedIn or shoot me an email if you guys have any further questions.
Thank you very much, Akbar. So now we have a couple of questions in the Q&A. Are you able to read them?
Uh-huh.
Okay, great.
Yeah. So let me read the first one. How important is it for data analytics to have skills in NoSQL? So this is a really good question. So these days, because the data that is, an analyst generally, at least that I know of, deal with data in data lakes. And they basically deal with data with SQL databases, with NoSQL databases, and primarily with NoSQL databases these days. So I would say, at least at Intuit, the data analysts are transitioning from a mindset of querying on SQL databases and moving to NoSQL databases. So yes, to answer your question, the tool I am not really sure of. What I can do is I will talk to some data analysts in my company or that I know of, and what tool are they using on top of a NoSQL database to query the data, and I can get back to you. For SQL databases, I have just seen them run SQL queries on top of data lake to fetch the data.
All right. Are there any other questions? If you've got any other questions, attendees, please post them in the session Q&A. So there's one more. I think we have time for one more.
Yep. You talked about polyglot persistence. Are you using only Elasticsearch for all use cases today at QuickBooks? Are these use cases, there use cases it is not good for? Yes, as I said, we have to use the right technology for the right use case. So for example, if we did not have a use case for search or aggregations or even time series, we would not go with Elasticsearch. There are use cases where we are using Dynamo or we are using Cassandra to do polyglot persistence, and we are not using Elasticsearch. So Elasticsearch is really good with searching aggregation. So we are using it for that, but it is not a one hammer for all polyglot persistent use cases. You have to see what the use cases that you're solving for in the product or for the platform, and then decide the tool that you want to use.
Great. Thank you. Thank you, Akbar. So thank you, Akbar, for your presentation. I appreciate all the attendees for their questions and their interactions during this session. Please contact the speakers if you have further questions on this topic. And please provide your comments and feedback to us on the community board or start a discussion there to connect with others in the DataCon LA 2020 community. Thank you very much for joining today's presentation, and I hope you can gain some insights from this session. And everybody have a wonderful day, and thank you for being a part of this year's DataCon LA. Bye, everyone.
Yep. Thank you, everyone, for attending.